Hi everyone, welcome back to all of you on my YouTube channel. I'm Ankit Mishra. I'm teaching for GATE Chemical Engineering since last 5 years. So I have started this lecture for GATE 2026. So you can go through my playlist of process rhymes and control, and you can see I'm uploading all of these video in a series manner so that you the subsequent topic will be very easy for you to understand. So in the previous lecture, you can see I've discussed about the transfer function for the mercury thermometer, and already I have derived these things where we have seen that the rate of energy in is equals to rate of change of internal energy for the mercury, and here you can see that qt is the rate of heat transfer, that will be equals to mc dt by dt, where t temperature is temperature of mercury thermometer, right? And after that we have derived the time constant for the mercury thermometer, that is tau, which is mc by ha. And from there, while doing the energy balance, we have got equation 3, that is a first order differential equation, and if we take the Laplace transform of equation 3, we will be getting this kind of transfer function where ys by xs, ys is the temperature of mercury and xs is the uh, step input or kind of input that you are providing for the mercury thermometer. And from there you can see that let's say if I am providing a step input of magnitude m, and we will be doing the Laplace inverse, and finally you will be getting a transfer formula for output response, that is yt minus ys, that is equals to m into 1 minus e to the minus t by tau, where tau is your time constant, yt is the temperature shown by mercury thermometer at a particular time, and ys is the initial steady state value. So let's say if ys small ys is 0, then yt is equals to m into 1 minus e to the minus t by tau. Okay, so finally now in the here I'm going to start with these things, uh, transfer function of continuously STR tank reactor, right? So let's try to understand these things today. It's a very important topic also. So in GATE 2025, you can see the question has been asked on this particular topic, the on transfer function of CSTR. So it's very important. So here this year it was a first order, the reaction that was occurring in the CSTR was first order. So again in future it can be asked for the second order, any zeroth order, something like that. So let's try to understand the transfer function of transfer function for CSTR, right? So let's say you have this CSTR, right? And there is inlet and there is outlet, right? So I'm assuming the volume of CSTR is V, and volumetric flow rate is V naught, and initial concentration of reactant is Ca naught. So if I'm assuming a reaction A is getting converted into product V, having order of reaction is N and rate constant is K, right? So inlet concentration I'm assuming is N and outlet concentration is Ca. So if I'm talking about the space time for the CSTR, tau can be written as V divided by V naught. So that is volume of the CSTR divided by volumetric flow rate. Okay, so here you can see that if I am writing the reaction minus of Ra, that can be written as Kca. Since I am assuming the first order reaction for the simplest case, that's why I will be driving these things for this. And also I am assuming there will be constant volume, I am assuming the constant volume reaction system, CVRS system, where volume is not going to vary. That means I am considering the liquid phase reaction where A and B both are the liquid product, right? Sorry, a reactant and product in the liquid phase. Okay, so if we know, if you go to the property of the continuously stirred tank reactor, so the process parameter inside the reactor will be same at the outlet. So if the temperature here is T, here temperature will be T, and at the exit also T. And if I am assuming concentration at the exit is Ca, so here concentration will be Ca and Ca, something like that. So you must be knowing these things from your chemical reaction engineering. But now the thing is that I want to calculate the concentration of reactant at any particular time, right? So the main objective of doing this particular thing is to understand the dynamics of the outlet concentration of the CSTR at the exit, right? Something like that. So Ca naught, obviously I have told you, that is the inlet concentration, and Ca at T is the exit concentration, and V naught is the volumetric flow rate. Now if I want to write the material balance for the CSTR, so what I can write, d by dt of Ca into V, that can be written as V naught Ca naught in volumetric, sorry, molar flow rate in minus out, that is V naught Ca, since I am considering V naught is the constant, and minus there is a reaction. Is that clear? That is equals to rate of accumulation, right? So again I can write d by dt of Ca into V, right? That is equals to V naught Ca naught minus V naught Ca minus Kca. Is that clear? And after this, since I am assuming this is a constant volume reaction system, so I'll take volume as a constant, so I can write dCa by dt, that is equals to V naught Ca naught minus V naught Ca minus Kca. Is that clear? So now we'll divide both sides by V, and we'll get that, let's say, dCa divided by dt, that is equals to V naught divided by V Ca naught minus V naught divided by V Ca minus K divided by V Ca. And obviously already I have derived, sorry, already I have discussed that what is tau. Tau is the space time, that is called as the V divided by V naught. So if I'll substitute these things in the above equation, so what I can write, that dCa by dt, that is equals to 1 by tau into Ca naught minus 1 by tau Ca minus K by V Ca. Is that clear? So let's say we have three terms of regarding Ca. That this one is Ca, this one is Ca. So let's try to club this term together. So I can write dCa by dt plus, if I take Ca common here, so what I can write, 1 upon tau plus K by V. Is that clear? 1 upon tau and K by V. Okay. 1 upon tau and K by V. Okay, sorry. So there will be minus Ra into V, in minus out. So there will be a multiplication of capital V here in rate of reaction term. Sorry for that. Yeah. So if you will multiply these things, this will get cancelled out here, and finally you will left with only K. So Kca and K, right? And that will be equals to Ca naught divided by tau. This is very important to understand this thing. Now let's say I am assuming this one is equation first for this particular lecture only. So now taking Laplace of equation first. So what I can say, Laplace of dCa by dt plus 1 upon tau plus K, this is a constant term, and then I can take Laplace of Ca, that is equals to Ca naught by tau, and that I can take Laplace of Ca naught by tau. Okay, so if you see the Laplace of your these things differential, you if you recall these things, so I can write S into CAS plus CA 0 plus 1 upon tau plus K CAS, that is equals to again 1 upon tau Ca naught S. Right, now we have written all of these terms in S domain. Now you can see Ca0 will be 0. So now if I take Ca S common, so that can be written as S plus 1 by tau plus K, that is equals to 1 by tau Ca naught S. Now, so what is transfer function? So the transfer function for CSTR can be written as obviously output divided by input, CAS divided by Ca naught S. So how can we get it? So in both sides I'll divide by Ca naught. So let's see, if I am assuming this one is my equation second for today's lecture, so I can write CAS divided by Ca naught S, that is equals to 1 upon tau divided by S plus 1 upon tau plus K. Is that clear? So now this is just a transfer function. Now if you want to again calculate these things or simplify these things, so I can write CAS divided by Ca naught S, that is equals to obviously this is 1 by tau and tau s plus k tau divided by tau. So this tau and tau will get cancelled out. So finally you will be left with CAS divided by CA naught s, that will be equals to 1 upon tau s plus k tau. Is that clear? Tau s upon k tau. So this will be your transfer function. So again, either if you want to show this transfer function in this form, that is also fine. If you want to show this transfer function in this form, that is also fine. So both of these things are same, just a simplification of mathematics I have done from equation 3rd to equation 4. So I will be assuming this one is my equation 4. And now let's say if in the continuous stir tank reactor at the inlet that is having magnitude is m by s. So now we can calculate CAS, that is equals to m divided by s into what, 1 upon tau s plus k tau. So based on this particular formula, this here question have been asked in question has been asked in GATE 2025. And now what we can do, so we can take Laplace inverse. So if you take the Laplace inverse, then it will convert the s domain into t domain. So I'll take Laplace inverse of m by s into 1 by tau s plus k tau. So now already in my previous lecture I have taught about how to take the Laplace of the function. If this is in this form, you can take the partial fraction the way we used to do these things for the integration in class 12 only. And once you have calculated the value of the constant, you can calculate the value of concentration of A at any particular time, something like that. Okay, so this is how this thing works. So in next lecture I'll be talking about the derivation of transfer function for tanks. So single tank, again interacting system, non-interacting system, and also the transfer function of plug flow reactor. Okay, and after that also I'll be deriving the transfer function for the energy system. Okay, so stay connected with my lecture, and continuously I'm putting the lecture for process and control these days. So definitely this lecture will be very helpful for you all for GATE 2026 as well as BARC examination. Okay, thank you, see you in the next lecture.